All right, so now we're going to talk a little bit more. That's the end of context for the moment. We want to talk about now how to start to use the math objects within your WeBWorK problems. There's an important distinction to make between two different kinds of formulas that go on in your problem. Well, a WeBWorK problem is a program. It's written in this PG Perl language. But we want to think about our problem as actually code, as a program that runs to create the text of the problem and to check the answers. And that has some implications. That means that there are two ways that you're dealing with formulas in your problem. One of those are formulas like those typed by the student. These are the things that they're using as correct answers and that students are typing. But there's a whole other kind of formula that they're using, which is formulas that you write to compute values or to check the student's answer and so forth. These are the formulas that are part of the program you're writing, that are not a character string that a student types or one that represents the correct answer. It's the code of the problem itself. And these don't work the same way, so you have to keep the distinction between the two in mind. The first of these are handled by MathObjects and usually come from a quoted string that represents the formula in question. It's like the things you're entering as the answers in PGML. When you say, underscores make a blank, and then in the braces you put quotes 1 plus x squared, end quotes, that's an answer that MathObjects is going to parse using the current context and produce a math object internally to represent that answer. That's one way that formulas are used. Basically, they come from these quoted strings. The other kind are the Perl formulas that are part of the Perl program. They don't come from quoted strings. They come from the Perl language itself. Math objects can be involved in those if you set variables to contain math objects, but the formulas themselves are being parsed by Perl, not the math objects. And that distinction is important because the context is a math object thing. It's not a Perl thing. It doesn't control the Perl functions. So these two ways of using formulas in your programs work differently, and you have to make sure you keep the distinction separate in your head. When I talked about the context, mostly that's talking about the first kind of these things. And what we're about to do is mostly the second kind of thing. So when we're talking about Perl variables with a $A, that kind of stuff, that's being governed by the Perl language. When you're talking about compute with a string inside of it, or PGML where you've given an answer as a character string, that's the MathObject stuff. So keep those two distinctions in mind. And it's subtle what the differences are. So these two answers operate very differently from each other. These two things say the same question, but the two answers are very different. One of these is in quotes and one of these isn't. The first of these is a Perl formula, not a MathObject formula. The second is the MathObject formula. And so what happens is, for this first one, square root of 3 divided by 2 is handled by Perl. That operation is performed before the MathObject library is involved at all. Whereas the second one, this string, gets computed through MathObjects. So the parsing that's involved in understanding this string is the one that's controlled by the context. The parsing that's involved to understand this formula is what is Perl formulas, which does not involve the context. We've got to be a little careful about that. And there's a distinction here in what the student will see when they ask for the correct answers. Both of these will properly evaluate the student answer. It's the same thing in both cases. Square root of 3 over 2 is the correct answer, and both will grade that correctly. But the distinction here is what happens when they ask for a correct answer. And here's the difference. The first one is computed down to a numeric value, 0.866025, before math objects get created for it, and then that is what the correct answer is, 0.8660025, which is a correct answer, but it's not a very symbolic one. The second one, because it was in a string first, MathObjects is the one that's parsing it, it can create the nicely formatted version of that as a text string or as a algebra string, and represent it as square root of 3 over 2 in the correct answer. So that's an important difference to note. Frequently, if you do Perl computation, it's perfectly correct, but you're going to get numeric answers, pure numeric answers. Things that happen in MathObjects can retain their algebra format. So that's one distinction between those two forms. If you don't understand that now, don't worry about it too much, but it's something that will come up in some of your questions, I'm sure. Here's another one to keep in mind. Perl does not handle implicit multiplication, but MathObjects parser does. So for a math object, you could say 5 pi over 3. But you can't say that in Perl. Perl, you have to say 5 times pi over 3. So that star for multiplication is required if you don't have the quotation marks around it, and where it's optional in this case. The same thing, MathObject doesn't handle MathObjects handles points, vectors, and lists, but Perl doesn't. So I can say in quotation marks these angle brackets 1, 2, 3 as a vector, but I can't do that in Perl. The best I could do is call vector 1, 2, 3, a function to create this vector. So if you want to represent your answers in the way the student will type it, the student is never going to type vector 1, 2, 3. That's not something they get to type. They would type angle brackets 1, 2, 3. So if you want to keep what you're doing and to be the same as what the students are doing, use the MathObject approach rather than the Perl. All right, so how do you do this? Well, you're using MathObjects to create stuff in the Perl language, and so there is a special function that says take one of these strings and turn it into a math object, and that function is compute. Compute takes a string, like 1 plus square root of 5 over 2, and parses it using the current context. All the things that are defined there are allowed in this string, and then produces the corresponding math object for it, in this case, a real number. In the correct context, 3 minus 2i is a complex number, and compute will return a complex value, which we store in the variable z. If you want an infinity, here's minus infinity, and that gets computed and turned into a variable that I can use in my Perl program. Again, in the correct context, parenthesis 2, comma 0, comma minus 1, close paren, is a point, and I can compute that string into an actual point object to use in my program to check the answers. Here's a vector. This is math object notation for a 2 by 2 matrix. Matrices are given by rows. So this is a row that consists of 1, 0, followed by a second row consisting of 0, 1, and the outer brackets make this a matrix. So that's a matrix object. Here's an interval, minus infinity open-ended on one side and closed-ended at 3 at the other side, so that's an interval. Here's a union of 2 intervals. This is a set of 3 real numbers. This is the word none. This is a list of 2 numbers. And this is a formula, 1 plus x squared. So all of those things can be obtained using the compute function. And we assign the result to a variable so that we can use the object later on. You don't need to specify the type of the object. The context does that for you. And compute will figure it out on its own. There's another advantage to compute that we'll talk about in a little bit. But basically, you simply say turn a math object string into the actual internal representation of that object, which we store. And it can be things like real numbers, complex numbers, points, and so on. When you use PGML to provide a string as an answer, PGML uses compute to turn it into a math object. So this is doing exactly, this is just leaving out the word compute because PGML will do that for you. And similarly, when a student enters an answer, compute is used to evaluate that. So it's exactly the same parsing that's done for your answers and the student's answers. So there's no chance of there being any inconsistency between them. And the resulting math object is compared to this correct answers math object to determine if they're correct or not. So all of these are governed by the context. It's also possible to use what's called a constructor function to create an instance of a type. Rather than parsing a string, you could just say real and pass it a Perl real number, 25.238, and turn it into a math object real number. If you want a complex number, you could say complex 1, comma, square root of 5. This would be like 1 plus square root of 5i. Infinity is infinity. This is a point. This is a vector. This is a matrix with 3 rows. An interval, you have to tell whether it's open or closed at its ends, plus its points. You could take a union of intervals, sets, and so forth. So there's strings and lists and formulas. So you may see these in problems that we use, but compute is usually preferable unless you're creating these objects on the fly. For example, if you're figuring out the values for a point, you want to make a point out of $A, $B, $C, then point $A, $B, $C is a straightforward, easy way to do that, rather than putting the A's into a string and so forth. So depending on your needs, these constructing functions can be useful. But if you're just taking an answer like a string, use compute because you don't have to worry about the type. The constructor functions also take a string if you really want. So complex 1 plus 5i is essentially the same as compute 1 plus 5i, or vector, and so forth. So these things are easy ways to get unions and lists. You can make a list that you represent as a list, the same way you the student would type it. And some of these things that take multiple values like 5, minus 3, minus 2, 3, so forth, you can put those in square brackets as an array if you want. Those of you who use Perl may find that useful. Those of you who aren't very versed at Perl, don't worry about that. All right. There are a bunch of predefined constants from MathObjects. One of these is pi, and one of these is infinity. So you could say Q is pi over 6, and pi is already a real math object, and dividing that by 6 gets you another real math object. So Q is a math object in this case. Pi is minus infinity. Here is a identity matrix that's 3 by 3. So value matrix is the Perl class that actually handles matrices. This says call a method of that object. Method is called I for identity matrix. And the number you pass it is the size of the matrix, square matrix, 3 by 3 identity matrix. The empty set can be produced simply by calling set with nothing in it, or by computing an empty set. This is how a student would enter an empty set in the answer to a problem, is by open and close parentheses. Just as an aside, Gavin and Paul and folks, if there are questions that are coming up, I'm not reading them. I see you're taking care of them. If there's anything I need to answer, let me know. Okay, formulas. Formulas can have values that are any type. The result of a formula can be a matrix, or a vector, or an interval even. So a formula can have values that are any type, even in intervals and matrices. So here's a formula that returns a point. Depending on the value of t, we'll get a triple of real numbers. Here's a formula that is a vector-valued formula. It takes a point plus t times a vector. So that's a parametric line. Here is a formula that is a list. That's just the value x and 3x and minus 2x, depending on what x is. Here's a formula whose value is an interval. Different x's get you different intervals. And here's a formula whose value is a matrix, 2 by 2 matrix. So you can have formulas produce any kind of result. The variables for formulas can also be of various types. So formulas have variables in nearly anything, including complex numbers or even vectors. So in the complex context, this one says I'm using complex numbers. There's a predefined variable z that's a complex number. So this formula is a formula on complex values, z squared plus 2 times the complex sign of the complex number z. So you can use complex numbers as your variables. Here I'm going to use vector context, and I'm going to take the variables and add a new variable r, and that variable, it has type vector 3D, so it's a vector with 3 coordinates. And now r is a variable in my context, so 2r over norm r is a formula that takes a vector as its input r and returns a vector in this case. So you can use variables of practically any type that you want. You can even have matrix valued variables if you want. All right, so in formula, and as we go through this, we're going to talk about some of the complexities that go on here. There's a difference between these two expressions, formula 3.14 and compute 3.14. Here's the difference. The first is a formula. It's a function. It is a constant valued function. Its value for any input is 3.14. The second is a math object equivalent to the real number 3.14. It's not a function, not a formula. And that makes a difference. The fact that this is a constant value formula is different from a real number, makes a difference, particularly in the error messages that are used when answer checking is done. So for example, if I were to type an x as if I used the result of compute and asked that as an answer in a problem, if I type an x here, it should say, your number looks like a formula, but I expect it to be a number. Your answer isn't a number, it looks like a formula that returns a number. Whereas on the left-hand side, with the formula 3.14, x is a valid formula, so you should not get any error message for that one. This one just says it's incorrect. It's incorrect as a formula, but you don't get any of the helpful information you would get from computing this as a number. It doesn't tell you it's not a number. Worse yet, you'll get some wrong information if you were to, for example, make this be, let's see, something like a list. You have this be a list of things. As your answer isn't a formula that returns a number, it looks like a list of numbers. So if you were actually thinking about this as a single number, and you were wanting students to think of this as a number, by putting formula here means you're going to tell them you're thinking about this as a formula. And so it's going to say you want a formula that returns a number, not just a number here. So you have told them the wrong information. You want to avoid that. So you don't want to use formula for constant functions unless you really mean it to be a constant function. So be careful about how you use formula or compute or other kinds of things, or real or so, or whatever the other values are here. These have differences, have consequences to the error messages that get produced. All right, similarly, there's a difference between real 3.14 and list 3.14. The list is a list of numbers, and the real number is a single number. So, for example, if I type 2, 3 as the answer for the real number, it should say your answer isn't a number, it looks like a list of numbers. Whereas if I put 2, 3 in this list, it'll say it's incorrect. It's an incorrect list. The list I'm looking for is 3.14. So again, using these things incorrectly will mean that you don't give the students the help that they could have. You want to use the correct type of object for the thing you're talking about. Now, if your answer was saying find all the numbers, all the places where this function is undefined, you would want to use a list, even if there was only one. You would want to use this form in that case because you don't want to say that it's just one number. You want to allow the students to enter several numbers if they think there are several places. So there are situations you use list of a single number. But if it's actually that you want a specific number, don't use a list. Use the real number that way because these things are different. All right, so these are some of the subtleties that you have to take into account. So when I say think about the error messages that the students will get for wrong answers, this is the kind of thing I mean. Singleton list exercise. So here's something I want you to do. So I want you to investigate the difference between these two math objects, the list containing the point 3, minus 1, 2, and the point 3, minus 1, 2. I see that a number of people have put messages out saying some of the things that they found that were different. And these are all excellent. So one of them said that if both answers are entered with square brackets, they're both graded as correct. I think in the list context, points can be entered in with square brackets. In the point context that these are in, those both, there are no matrices, so they produce points. If I enter the list 1 as 3 minus 1, 2, it is graded as correct. If I enter, okay, so if you've entered vectors here, 3 minus 1, 2, in both of these, one of them gets graded correctly and one of them doesn't. So this one gets graded correct. The other one says it doesn't look like a point. Yeah. Turns out that in the list processing, there's some type coercion going on. If things could be converted from one to another, they get converted. So vector here actually gets converted to a point in that case. There is, let's see, if I enter both as without the brackets, the one is, they're both incorrect, but the messages are different. So what do we get for these? Okay, so the one about the point says your answer isn't a point, it looks like a list. The second one is a list, and each entry in it is a number, so each number is compared to see if it's the correct point. So each number says it's not a point. Your first value isn't a point, second value isn't a point, the third value isn't a point. So this was supposed to be a list of points. Instead, you gave a list of numbers. So that's good. Let's see. The point solution recognizes when there's an incorrect number of points. So if we put in the wrong number of points, number of coordinates, and check that, you'll get the number of coordinates is incorrect for that one, but not for this, because that list could be a list of points of various sizes. It doesn't know what the conditions are for that point. Let's see. If you enter them in the wrong order, you get a warning in one case and not in the other. So if you have the wrong coordinates, the second one tells you the coordinates are wrong, the first one does not. Again, it doesn't know which point in your list of points the student's answer is supposed to match against. So there are issues like that. So those are excellent. One last thing. When I enter just a number, I get the same error for both. Your answer is not a point. Yeah, so that's a tougher question. If you put just a number here, what do you get? Your answer isn't a point. It looks like a number. The answer isn't a point. It looks like a number. Well, again, this is the same message that you were getting earlier where it was your first answer isn't a point. It looks like a number. There's only one here, so there's no reason to say your first answer in this case. So I think these are correct. All right. So this is saying, the list of the items in this list should be points. The Perl operators are overloaded so that they work with math objects in a natural way. That means once you've got a math object, you can use Perl formulas to manipulate it. So here z gets to be the complex number 2 plus 3I. Again, this is in Perl here, so that star has to be there. This is part of the program. It's not an answer a student would type. They could have typed 2 plus 3I. But once you have this variable $z, you can create $w using 2 times z plus the conjugate of z. So once you have a math object, you can manipulate it within your Perl program as you would any other variable. Again, a vector, if you have a vector, you can take 3 times the vector or take the unit vector in that direction. Here the x is acting as cross product and the dot is acting as dot product between vectors. Here's a column vector v and a matrix 2 by 2 matrix. This is matrix vector multiplication, and here is vector squaring. That is, a matrix square, which would be matrix times itself. So you can manipulate these things then as true mathematical objects. You can do the same thing with things like intervals and sets. To make yourself an interval, you can take that interval and add to it a set. That's the same thing as a union of this interval with that set. Here's a union that you can create with that one. You can set up a variable to be all of the real numbers, that is the interval from minus infinity to infinity, and you could take that variable and subtract the set 0, set containing the variable 0, and you'll get the union of minus infinity to 0 together with 0 to infinity. And a student could get that by typing in a expression like r minus the set containing 0, because r is predefined in the interval context as minus infinity to infinity. That's another way to get that same one. You can do your computation in the MathObject string or in Perl formulas. This is that distinction between the two forms. You can do it in either way. Complex numbers, again, can be created using the predefined value I. So 1 plus square root of 5 times I. But because of the way Perl works, minus I, you need to put a space there or put parentheses around it. That's in a Perl formula, not in the student answer or inside compute. I just want to point that out. Those are restrictions within the Perl programming language. Students would still type these in the natural way. So you would want to say 1 minus I, not 1 minus I. And that has to do with the way Perl works. And again, Perl does not have implied multiplication, so you would need to put in 2 times I, not just the 2I that a student would type in their answer. In vector context, I, j, and k are the coordinate unit vectors, so 3 times I minus 5 times j plus k is perfectly allowed. Notice that the same restrictions about I and j will affect I, j, and k here. You have to put spaces and all stars if you want to do multiplication and subtraction. All right. Objects get promoted from one class to another automatically. We saw that a little bit in that list context where the square brackets were, where the vector notation was turned into a point within the list context. Well, objects are promoted from one class to another automatically as they are needed. For instance, a real will be promoted to a complex when they're added together, and a point is converted to a vector when they're added together. So because the list object was comparing a point to a vector, it said, I will promote the point to the vector and compare those. So if you have something like a point, and you have a vector, then the point plus 3 times the vector ends up with a vector result because the point gets promoted up to a vector. You end up with the vector 6, 4, minus 7. That gets done automatically. You can force this kind of thing to happen by taking an object and putting it into the constructor function for a different type of object. So suppose you had a point 317, you could force it to become a vector by putting vector around that value. And that will end up being the vector 317. So you can coerce the type yourself. Here, if z is a complex number 3, 0, then putting real on this will try to convert that complex number to a real number. In this case, that can be done, and it's equivalent to real 3. This is not taking the real part of that complex number. It's converting the complex number to the real number, so that the imaginary part has to be 0 for this to work. If it's non-zero, you'll get an error message, can't convert that number to a real. If you want to take the real and imaginary parts, there are functions for doing that, RE and IM for doing that. But that's not what this does. This is type conversion. This is converting one object to another type. Formulas. If an argument to a constructor function is a formula, then what you get back is a formula of the given type rather than a constant. So if you have f as a formula 1 plus x, you take vector 1 $f3, the result is essentially formula 1 plus x3. It's essentially doing that. So you get back a formula object that returns the type that you were talking about. So this union between an open interval 1, 2 and the closed interval x to 2x is essentially the same as the formula you would get by taking a union as a formula. So things that have formulas in them automatically become formulas themselves. That's useful in the following sense. When a formula is used in an operand in a Perl formula, the result would be another formula. For instance, if I have $f is the formula x squared plus 2x, and I make g be 3 times f plus 1, that's equivalent to having said the formula 3 times the quantity x squared plus 2x plus 1. So you can take your formulas and operate on them just as you would in a mathematical setting, and you'll get the right thing in the end. Similarly, if I had formula x squared and I stuck that into sine, I get back what is essentially the formula sine of x squared. So g will be the formula that's sine of x squared, as you would expect from this. So these do the right thing. And one useful possibility of that is for creating things like having just x be the formula x, and then dealing with $sign x as though it was the variable. This gets you a polynomial, a formula, and this gets you sine of x squared. So that's essentially the same as doing those. So you can make a single formula $sign x and have it used to create more complicated formulas like those polynomials. That's useful in particular in checking student answers where you get the student's result as a formula. You don't know what formula they used. You can manipulate it using your Perl formulas just as you would a variable. So that's very convenient. All right, so the last exercise for this afternoon, for this morning, before our break, is to look at this one that says find 3 different ways to assign $sign f the formula 2x minus 1 squared plus sine of x minus 1 over x plus 1. And use the MathObjects lab, which is problem 48. So here, what you have is a place where you can just type some stuff in, like $sign x is formula x plus 1. And if you hit process commands, you'll get the formula up here. So everybody take 5 and figure out 3 different ways to, 3 different ways to get this formula as a $sign f. Okay, so she made g the formula x plus 1, h the formula x, g x minus 1, h x plus 1, and did a formula involving that. That's great. We get the divide. Okay. Another one says make a formula x, and then make f and g be x minus 1, x plus 1, and do a formula based on that. Also excellent. Of course, you could write $sign f as formula and make the long algebra expression for this. So there are several ways to do that. That's excellent. There's the one. Okay, so Sean says just make formula with the whole algebra expression. That's also correct. There are a variety of approaches to that. All right, very good. Well done. Right, a couple of warnings, and then we'll call it a morning. Again, there's this distinction between the Perl program formulas and the MathObject student answer formulas. In Perl, exponentiation, as we've seen, is done by 2 stars, not by the hat. The hat in Perl means something else. It means bitwise exclusive OR, for those of you who knows what that means. It's not exponentiation. If you use it in a Perl program, you will not usually get an error message because it's defined. It has a meaning there, and so it'll produce the wrong answer silently. If it's used with a math object, however, you'll get a message about it because MathObject will tell you, and a MathObject doesn't have bitwise exclusive OR. So it'll tell you about it. But inside Perl, you have to be careful about that. So you want to be careful in, again, being aware of when you're using Perl programming language versus the algebra language for a student answer or a compute, a math object call. Second one is that Perl can overload operators that it knows about. So it can't use any of MathObject's non-standard ones that are available in formulas or in student answers. For example, the vector cross product for a student is written as a greater than sign, less than sign. Looks kind of like a cross in student answers and professor's formulas. But this is not a valid Perl operator, so you can't use it directly in Perl expressions. The X operator in Perl is overloaded to do vector cross product, and dot is overloaded to perform dot product, but you can't use an X in your student answers. That's because in Perl, the variables all start with dollar signs, so you can distinguish them from the variable X. But in MathObjects, the variables don't have dollar signs, and so this X would be a variable X, not an operator. So there's differences between these two settings that you have to be worried about. So be careful again about where you're working. And finally, the precedence of the Perl operators are not able to be changed. That is, the order in which operators are done are built into Perl. You can't alter them. But in MathObjects, you can. You could actually make plus and minus be done after multiplication if you wanted to. So be careful. This first compute uses the MathObject context. And whatever settings are there about what functions you can use and what operators you can use and what precedences they have is defined in the context. Whereas this one, what's happening is Perl is handling this expression before MathObjects gets it. This gets computed to a single number that gets passed into real. And then it gets turned into a math object. So those ones use the precedences and meanings in the Perl language, not in MathObjects. So be very careful about where you do these things. When you use quotation marks, when you don't use quotation marks, when you got compute and when you don't. So that's the big lesson for today. All right, this is the table of contents for the slides we've done. There are also two labs. The PG lab just lets you type in an expression and lets you get the result. So you could talk about vector 1, 2, 3, and this will produce the vector 1, 2, 3. So you can play around with PG there. This one is a problem lab. This lets you lay out an entire problem. So you could do something like load macros, pgml.pl. The basic macros are already loaded. And then do begin pgml and pgml. Put in here the answer is 1 plus x. And then when you press this, it will lay out the thing for you. So this is a way of kind of testing out problems without actually having to make a problem file and save it someplace and assign it to a problem set. This lets you experiment with MathObjects and the PG language and PGML. And then you can answer the question if you want. So X, I could submit the answers and it'll process it just like it would a regular problem. So this is a nice little lab to let you play without having to save things. But if you're writing something you want to keep, by all means, don't use this. Save the file someplace.